right? We have introduced the public key cryptography principles, and we have seen the most popular, widely deployed public key cryptography algorithm, that is the RSA algorithm, right? We have discussed the algorithm, three aspects of the algorithm. So what are the three aspects? Number one, the most important thing is the key generation. Then second one is the encryption process. Third one is the decryption. Okay. And RSA, we discussed, it is the block-based encryption algorithm, right? So when a sender wants to send a plain text, first of all, he has to convert that plain text into the block of numbers. Then choose the receiver's public key. For that particular purpose, every node has to generate the key pair, right? The public key and private key pair. So public and private key pair. The generation of public key and private key pair is one of the most important aspect of the any public key encryption algorithm, and obviously for that particular matter, even the RSA. We have seen in the yesterday's class how the public key would be generated. The pair would be generated with the help of the key generation algorithm, where through the random generator algorithm, every user first of all have to generate two large prime numbers P and Q, and from that calculate the N, then choose an E, and then calculate a D. Subsequently declare N comma E as the public key and keep the D as the private key. Okay, so once the public key and private key pair are generated, the sender would take the public key of the receiver and perform the encryption process. C is equal to plain text to the power E mod n. Upon receiving the ciphertext, the receiver would decrypt the message by performing C power D mod n, where the D is the private key of the receiver. This is the whole process of RSA generation, RSA key generation, encryption and decryption. We also discussed that the computational aspects of RSA algorithm. Okay, and upon understanding the computational aspects of RSA in comparison with the symmetric key algorithm, we also discussed where the public key would be applied. So the application of public key encryption algorithm also we discussed in the previous class. Okay, so essentially application of public key algorithm, for that matter RSA, okay, is not for encrypting the plain text, but for encrypting the symmetric key. Remember, the symmetric key is also called as the session key. Okay, so once the encryption of the session key is used, that means what actually we are doing is typically the plain text is encrypted through symmetric encryption algorithms. When the plain text is encrypted with the help of symmetric key algorithms, the challenging aspect of symmetric key is how do you exchange that particular symmetric key. So for that particular purpose, typically the RSA algorithm, or for that matter any public key algorithm, would be used, not for the encryption of the plain text. That's what we discussed in the previous class. Now, having discussed, we also know the security of the RSA algorithm. Okay, security of the RSA algorithm lies with the fact that we do not have a suitable or polynomially executable algorithms in a polynomial time to identify prime factors. We don't have algorithms. So The security of RSA lies with the fact that there are no algorithms to identify the prime factors. But having said that, is it that RSA cannot be broken, or RSA cannot be attacked? No, there are potential attacks on RSA. So if we notice what are the various attacks on RSA, there are various attacks. Number one, the most important attack is the factorization attack. Okay. When I say factorization attack, obviously, if there is an algorithm that is able to identify the prime factors of the large number, that means if you notice the public key, what is the public key of RSA? Typically, it is E comma N. Remember, N is known publicly. But what is not known publicly is the prime factors of N. So we know that N is equal to P star Q. Imagine if PQ are identified, then your calculation of D is very easy, right? So factorization attack is about identifying these prime factors. Remember, when I say that we don't have the algorithms to identify the prime factors, is it that we don't have algorithms? Yes, we have the algorithms, but those algorithms do not work for large numbers. Okay, when I say large numbers, we have seen the magnitude of such numbers, that is around 1024 bits and more. Okay, that means around 200 digits plus. Okay, 200 digits. Now imagine if I choose a prime, if I choose a number which is, say, take an example, 3 digits number, like in thousands, 4 digits number, 5 digit number, it is easily breakable. So the factorization attack is about how do I identify the prime factors, and if I choose a small number, obviously it is easy to factorize it. When I say the security of the RSA algorithm is with the fact that we don't have an algorithm to identify the prime factors, it is for the large numbers of around 200 digits plus or 1024 bits and more. So one is the factorization attack. Another one is, are you able to follow what we are discussing? Hello?
Yes, sir.
Next kind of attack is called chosen ciphertext attack. Okay. Chosen ciphertext attack is one of the interesting attack which we will be discussing. Then you have encryption exponent attack, encryption or decryption exponent attack. Again, when I say these exponents, it is with the small numbers. Okay. Then you have common modulus attacks. That means if many people choose the same common modulus of n, okay, so that also leads to the problem. Okay, so these are all various kinds of attack. Now let us understand one particular attack, which is the chosen cipher attack, which is not dealing with the security of the RSA algorithm. Remember, if you look at the first attack, the third attack or fourth attack, it is about the numbers that are involved. If I choose enough large numbers, I will be able to manage the first attack, third attack and fourth attack. But the second attack is one of the interesting attack called chosen ciphertext attack. Okay, what is chosen ciphertext attack? If you see, it is nothing to do with the RSA security. Okay, now imagine a scenario where Bob and Alice are communicating with each other. There is an attacker called Eve. Okay, Now what happened? Bob is sending a message to Alice using RSA algorithm. For that purpose, Alice is having PUA and PRA. That means the pair, public key and private key pair. And remember, Bob also would have public key and private key pair, right? And obviously Eve also will have public key and private key pair, right? Is it not? Hello?
Yes, sir.
Now the point is, okay, let me take another slide and then explain. So Bob and Alice, and you have Eve here. And Bob is having the pair PUB, PRP. Alice is having the pair PUA, PRA. And Eve is having the pair PUE, PRE. Okay. Now the point is, Bob wants to send a message to Alice. For that purpose, imagine Alice public key is E comma N. Okay. Now Bob will take the message M. The message Bob wants to send is M. So he is going to calculate ciphertext of the message as C is equal to M power E mod N. Correct?
Yes, sir.
So E and N are the public key of Alice. And Bob has calculated the ciphertext and wants to send this message to Alice. Okay. This is chosen ciphertext. Now the point is, when Bob is sending this message to Alice, remember the EN values are known not only to Bob but also to Eve. What Eve is doing, Eve has intercepted this particular message. Eve has intercepted this message and got C. Okay. Obviously, the C is the ciphertext. Eve cannot do anything. Now, what Eve is doing, Eve is choosing a random number called, say, X. Okay. Eve is choosing a random number X, which is belonging to the integer set of N. That means where he knows the N, he is taking an integer, a random integer in the integer set of Zn. Obviously, while he is choosing, he will choose an X such that X is having the multiplicative inverse. Okay. X is also having the multiplicative inverse. So he chooses such number of X. And then what he's going to do, he is going to calculate a Y. How he is calculating this Y? Y is equal to the C into, okay, C into, this is X, this is into, and okay, let me say put star, C star X power E mod N. Okay, this is how Eve is calculating a Y. C into X power E mod N. He chooses a random number X such that X is also having the multiplicative inverse. So he calculates a Y. Are you able to follow up to here?
Yes, sir.
Yes, sir.
Now what Eve is doing, he captured the C and calculated a random text by choosing a random integer. Okay, and he is going to send this Y to Alice. Okay, remember, if Alice decrypts C, what Alice will get? Alice will get M, right? If Alice decrypts C. Hello, are you able to follow?
Yes, sir.
Yes, sir.
Yes, sir.
If Alice decrypts C, that means if Alice decrypts C means what? He will decrypt it as C power D mod n, right? What is C power D mod n? What is C power D mod n?
The plain text that Bob sent.
What is that? That is M, right?
Yes, sir.
Now Alice is decrypting not C. Alice decrypts Y. What is Y? C into X power E mod n, correct? Hello?
Yes, sir.
So what Alice is going to do, Alice is going to perform the decryption. That means Y power D mod n. Because Alice received a ciphertext from Eve called Y. The ciphertext is Y. So obviously when he receives the ciphertext, he will try to decrypt it. The decryption process is Y power D mod n. So once he do that, he get some text called Z1, some text called Z. Okay. Is it not? Hello?
Yes, sir. Yes, sir.
Obviously, Alice will get some text called Z. And remember, would that be a plain text? Hello? Hello?
So it won't be the original message.
It will not be a plain text, right? It will not be a meaningful text. It will not be a plain text. It would be some scrambled text, right?
Yes, sir.
So Alice sees this Z and do not know what is this Z because it's a scrambled text. And remember, this step is very important. Imagine if Alice sends back that Z to Eve asking what is Z. Imagine if Alice is asking Eve what is Z. What Eve has got? What Eve has got?
Scrambled text.
Yeah, what is that?
Decrypted version of Y.
No, what is Eve? Eve got? What is that Eve got? What you said is correct, but what is that variable? It is Z, right?
Z. Yes.
Yeah. Now Eve got Z. Now remember, from Z, Eve will determine M. Eve will calculate M. How he calculates? What is Z? Z is nothing but Y power D mod n, right? What is Y? What is Y? C into X power E mod n. Correct? Hello?
Yes, sir.
What is Y? C into X power E mod n. Look at here. Y is equal to C into X power E mod n. Now this is nothing but C power D and X power E. And what is X power E power D?
And
Hello? Which is nothing but your X, right? Hello? Hello?
yes, sir.
Yes, sir.
C power D, X power ED means X because E and D are the multiplicative inverses, right? So what is C power D mod n? What is C power D mod n? Is nothing but X inverse Z, right? Z, now you've got X inverse, he get it because he has chosen an X such that it has the multiplicative inverse. From that, C power D mod n calculation is very easy. What is C power D mod n? What is C power D mod n?
Basically, Eve has
M.
the number n and she has the ciphertext, so it will be easy for her to get
Yeah,
key
so
D.
he got, no, what is C power D mod n? It is nothing but the M. Correct?
Yes, sir.
So now this is one of the interesting attack on the RSA in the sense that there is no factorization related problem. You have chosen a large prime factors. So absolutely there is no problem with regard to RSA algorithm security as such. But where is the loophole here? The loophole here is number one, Eve is able to capture C. That would be a loophole? No, in all practical applications, your ciphertext is freely available on net. Eve also knows E comma N, obviously, because E and N are the public key of Alice. Obviously, everybody knows. Now, where is the problem? The problem is when Alice has got a scrambled text of Z, Alice has asked Eve, what is this Z? Imagine if Alice has not asked Eve, what is Z? Would this attack is possible?
No, sir.
This attack will become possible if there is communication from Alice to Eve asking what is this Z?
Sir,
Okay.
but why would Alice ask Eve?
No, see, it is like this. It is like this. We are communicating with each other. I just said something. You do not know what is that, and obviously you will ask it, right?
Okay, sir.
So it is like this. If Alice responds to a scrambled text asking to identify what is that scrambled text, I got some message, and when I get a message, imagine if it is some plain text, I understand that yes, this is the message what the sender has sent. Now I got the scrambled text. Hey, what is this? When I ask, gone. It is quite natural, right? The human psychology, right? So the point is here the attack is possible. As I've said, attack is possible only if Alice responds to this message. If Alice do not respond to the message, there is no scope for the attack. If Alice do not respond to the message after decrypting the after decrypting Y, getting some random text of Z, if Alice do not respond to Eve asking, hey, what is this? This is the one you have sent? Or is it by chance during the communication, in the communication channel is something got I lost? Or whether my decryption is not correct? Or whether your encryption is not correct? Or some packets are lost in the middle? So it's quite natural, right? If you keep asking. So you ask, that's all gone. Okay, so this is called chosen ciphertext attack. The reason is the attacker has chosen the ciphertext and sent the message. And this kind of attacks, remember, are called side channel attack in the sense that they don't deal with security of the algorithm. Is it that anything related to security of the algorithm here? Whether your prime factors are small, whether your prime factors are large, or you don't have an algorithm to identify prime factors. Is it something like that? This particular attack? Hello?
No, sir.
This has nothing to do with that. Of course, it is based upon the fact that if you have your multiplicative inverse, and then if you get that response back, the attack is made possible. Okay, so this is a kind of attack called side channel attack in the sense that they don't deal with any, there are n number varieties of side channels attacks, and in fact it itself is a big ocean. The point is that attacker will make the attack not based upon the weakness in the algorithm, but rather by revealing or by leaking some kind of information about the crypto system. Okay, so such type of attacks are called side channel attacks. And remember, you design any sophisticated cryptography algorithm. Okay, so the side channel attacks are nothing to do with the security of the algorithm, but rather it is about the way things are getting implemented, the way things are leaking some information. Okay, so it is about such type of attacks. So that's the reason why in most of the security literature, in fact, the side channel attacks are having a lot of importance in the sense that, because of the information that is getting leaked. See, the algorithm implementation, these things are making the communication environment less secure. Okay, is that clear? No.
Sir, can you just explain this last step once, how we got X inverse Z from C to power D model?
Yeah, so if you notice C power D, X power ED, if you notice, it is C power D. I can write it as C power D. X power ED is X because E and D are multiplicative inverse, so you get X. So C power D into X mod N. Now the point is that I can calculate the C power D mod N as Z into X inverse. Okay, by taking X this side, X inverse Z. What is X inverse? The multiplicative inverse of X. Remember, while choosing X, Eve has chosen an X such that it has the multiplicative inverse. So he knows the multiplicative inverse of X, and obviously he got Z now. So X inverse Z is nothing but C power D mod N, which is nothing but the M. Okay, C power D mod N is nothing but your M, right? See here. So X, when you calculate X inverse Z, it is nothing but you are calculating C power D mod N, which is nothing but again M.
Okay, thank you, sir.
Okay. So this is how the RSA would be attacked. So the only way that you can prevent it is by ensuring that Alice is not responding. Alice is not responding to this type of messages. Okay. So next we go to the next algorithm called Diffie-Hellman key exchange algorithm. So this is another interesting algorithm of public key cryptography. In fact, it was the one which was published as the first public key cryptography algorithm. Okay. And the purpose of this Diffie-Hellman key exchange algorithm is, as the name itself is mentioning, it is to exchange the key. But where do you get the point of exchanging the key? Whenever you are performing symmetric encryption, you have the need to perform key exchange, right? So when Alice and Bob are communicating with each other through symmetric encryption, they need a common key, right? So Alice is sending something to Bob through symmetric encryption. They need a common key, which is K. Both should have that. Now the question is how the common key comes to both Alice and Bob. Or either Alice has to create a key and then encrypt it, the message, with the symmetric encryption algorithm such as AES, okay, or DES or whatever it is. Then send the ciphertext and then share the key with Bob. So that is the overhead. So what is the Diffie-Hellman exchange is doing is it is trying to establish the common key between Alice and Bob such that once the common key is established, they can perform the communication, secret communication using a symmetric algorithm such as AES. So only issue is how to have the common key. Now imagine if your Diffie-Hellman key exchange algorithm is able to handle that, you don't have a problem. Like RSA, the Diffie-Hellman key exchange algorithm is also having security rooted to one of the non-solvable problem. Okay, either I can say that it is not non-solvable problem, rather we don't have an algorithm to solve that particular problem. Computationally feasible algorithm we don't have. Like in the case of RSA, you don't have a computationally feasible algorithm to generate the large prime factors. In a similar manner, Diffie-Hellman also lies with the fact that there is no algorithm, there is no computationally feasible algorithm to solve discrete logarithmic problems. The strength of Diffie-Hellman key exchange lies with this particular fact that there is no algorithm that can solve discrete logarithmic problem in a polynomial time. So there is no such algorithm, and the strength of the Diffie-Hellman lies with that particular fact, with that particular concept. Let us proceed further. What is Diffie-Hellman key exchange? Before proceeding to the Diffie-Hellman key exchange, we need to understand a little few fundamental definitions. We know what is a prime number. For a prime number, there is a definition called primitive root of a prime number. Now, what is meant by primitive root of a prime number? Primitive root of a prime number is, imagine if the prime number is p, primitive root of that prime number p is the one whose powers modulo p generates the integers in the range from 1 to p minus 1. Okay, so primitive root of the prime number p is the one whose powers modulo, okay, whose powers modulo p generates the integers from the range 1 to p minus 1. Now let us take with an example. Imagine if a is the primitive root of a prime number p. You have a prime number p and a is its primitive root. Then what we said, the numbers whose powers modulo p. What is powers modulo p? A power 1 mod p, a power 2 mod p, a power 3 mod p, a power 4 mod p, and so on, a power p minus 1 mod p. These are the powers modulo p numbers. And remember, if they are distinct and they are the numbers in the range from 1 to p minus 1 in some order, then you call a is the primitive root of the prime number. Let us take one example. Imagine the prime number is 7 and 3 is the primitive root of 7. That means 3 power 1 mod 7, 3 square mod 7, 3 cube mod 7, 3 power 4 mod 7, 3 power 5 mod 7, and 3 power p minus 1. That means 3 power 6 mod 7. These are all the powers modulo p. And what is that these numbers are generating? The output. 3 mod 7 is 3, 3 square mod 7 2, 3 cube mod 7 6, 3 power mod 7, 3 power 4 mod 7 is 4, and 3 power 5 mod 7 is 5, and 3 power 6 mod 7 is 1. What are these numbers? These are the integers in the range 1 to p minus 1. What is p? 7. So it is, these are the numbers from 1 to 6. Okay. So that is the reason why you are saying 3 is the primitive root of 7. Are you able to follow? Is this definition clear?
Yes, sir.
Now, what is the algorithm? Diffie-Hellman algorithm. Let us see. Now imagine you have for any integer b, and you have a prime number p and its primitive root a. So you have a prime number p and its primitive root a. Then for any integer b, we can find an unique exponent I such that b is congruent to a power I mod p. Okay. Now the exponent I is referred as here discrete logarithm of b for the base a modulo p. And remember, we don't have any kind of an algorithm to calculate I. That means the discrete logarithm of b for the base a modulo p. We don't have the algorithm. Okay. So imagine you have a prime number p and you have its primitive root a. Then for any integer b, we can find an unique exponent I such that b is congruent to a power I mod p. Okay, you can find b if you have all this, but here exponent I is referred as the discrete logarithm of b for the base a modulo p, and it is written as I is equal to discrete logarithm of b at the base a modulo p. Okay, this is what it is written. Now let us see the algorithm. What is the exact algorithm of Diffie-Hellman key exchange? This is the Diffie-Hellman key exchange algorithm. Now there are two parties, Alice and Bob, as usual. So there are two publicly known prime numbers, publicly known numbers. One is p and a, where p is the prime number and a is its primitive root. Okay, so both these numbers are publicly known, the prime number and its primitive root. Now what Alice is doing, Alice is selecting a random integer xa which is less than the prime number and calculating ya. How she is calculating? Ya is equal to primitive root to the power random integer mod p. The primitive root of prime number a to the power random integer xa mod p. So now a has xa and ya. Similarly, the Bob is also choosing a random integer xb which is less than the prime number and calculating another number called yb. How he is calculating? Primitive root power xb mod p. Now b is also having the xb and yb pair. Now both Alice and Bob, what they do? They keep their xa, xb values as private and make ya, yb as public. Okay, so that means the public values of each other are known to others. So Alice public key ya is known to Bob. Similarly, Bob public key yb is known to Alice because they are made public. Remember, x values are kept secret, xa and xb. Now, having known the public value of the other node, each user is calculating a key. How they are calculating? Now Alice is calculating yb, which is the public key of Bob, to the power xa. What is xa? private key of Alice mod P. That is how Alice is calculating a key. Similarly, Bob is also calculating a key. How he is calculating? Public key of Alice power private key of Bob. At mod P, like how Alice is calculated. Public key of Bob power private key of Alice mod P. Both eventually leads to the common value K. Okay. Now, by performing this equation, both are having the common value K. So that means YB power XA mod P gives you the value which is equal to YA power XB mod P. This is what is Diffie-Hellman key exchange concept. Hello, are you able to follow?
Yes,
sir.
Can you derive how actually this? Can you please derive how this is coming? Like you take any one expression, which is say take an example, take an example YB power XA mod P. Please take and can you derive whether YB power XA mod P is equal to YA power XB mod P. Can you please derive both are same or not? That's what is that language. That's what is the algorithm says, right? When you calculate YB power XA mod P and when you calculate YA power XB mod P, both have the same value.
yes.
So please derive that. And then we will discuss it in the next class. So if you notice, the interesting of this algorithm is that key is exchanged actually.
I mean, actually the key is not exchanged, but in the broader picture, yeah, they both got the key.
They both have now the key, but actually key is not exchanged. That means in the communication channel, neither of the parties, either Alice or Bob, they have not sent the key, but they both have calculated. How they calculated? In fact, there is a common values that are available to both Alice and Bob, and then they have their own private values. From that, they have revealed the public values. And once the public values are known to the others, they are able to calculate the common key. Now the key is not actually exchanged, but rather it is got established between the parties. Now once you have the common key between the two parties, what they can do, they can communicate with each other using AES algorithm, right? Which is a symmetric key algorithm. Now both have the key, so Alice can send a message by encrypting the message with the key, and then Bob can receive it and decrypt that message with the key. Your fundamental problem of symmetric encryption is solved of having a common key, is it not? So that is the beauty of this particular algorithm, the Diffie-Hellman key exchange algorithm. Now the point is we need to know how actually both have got the common key. That is one point. The second point is that now both have got calculated it. Is it that the attacker cannot calculate the key? In order to calculate the key, what is that attacker needs and why he will not be able to calculate? What is the difficulty, or there is no algorithm? So these are the interesting things that I think we will be discussing it in the next class. Hello?
Okay, sir.
Yes.
So